at the Japan Freight Railway Company for 27 years in various branches and headquarters, and he is now currently a general manager in the engineering and planning department. And today he will be giving us a talk entitled Applying New Technologies to Freight Railway Operations.
นี่ดูอันนี้หลักๆดูคนเห็นยังไงสิ
อะไรนะคะ Sorry. Okay, so Mr. Osabo, please.
Okay, please wait a minute. So I start my presentation. My name is Takaaki Otsubo. I work for Japan Freight Railway Company and serves as General Manager of the Technical Planning Department. Today, under the title of Applying New Technologies to Freight Railway Operations, I would like to talk about JR Freight's initiatives for sensors and IoT technologies. Let me show the outline of my presentation. First, I introduce my company. Second, work improvement of container stations. Third, handbrake detection system. Fourth, remote monitoring system. Finally, I would like to tell you about what we want to do for realization of smart freight stations. So let me introduce our company first. The Japan Railways Group was born in 1987 by splitting and privatizing the Japan National Railways. We are one of the 7 companies comprising the JR Group and the single railway freight company operating throughout Japan. We have around 7,000 freight cars running a total of 8,000 kilometers of operating tracks. There are 241 freight stations nationwide, from Hokkaido to Kyushu, operated by 5,400 of our employees. Roughly speaking, 5% of Japan's annual domestic freight transportation is carried by train. From the total domestic freight transport by train, 99% is carried by our company. So, I would like to talk about improving operations at container stations. This photo shows the Tokyo Freight Terminal, the largest freight station in Japan, located in the capital city of Tokyo. In this station, both departures and arrivals handled an average of 7,000 tons per day. Inside the station, the general logistics facility, Tokyo Railgate East, was born this year. It is a huge logistics facility inside the freight station, with a total floor area of about 174,000 square meters. One train has max 26 freight cars. In the case of this station, there are 560 meters long loading platform so that 26 freight cars can be loaded and unloaded at a time. There are 10 platforms back to back. There are two main types of transport forms: container transportation and car handling transportation. Over the past 15 years, transportation by car has declined significantly, and container transportation has grown remarkably. Currently, 70% of the cargo carried by our company is container transportation. A wide variety of items are transported in containers, including paper, food products, food cargo, courier services, agriculture products, and so on. There are three types of container size: 12 feet, 20 feet, and 30 feet. Over 95% of our containers are 12 feet containers, which uses anchor locks, and 5 containers can be loaded to each car. If you are a customer, there are two options. One is to make your own private specified container, and we will carry it to your destination. Second option is to rent a container from us. We operate about 78,000 containers, and around 80% is owned by our company. All loading and unloading of containers is done by forklifts. Forklifts are divided into three types. On the left is a forklift for 12 feet containers with a maximum load of 8 tons. In the middle is a forklift for 20 feet containers with a maximum load of 15 tons. On the right is a top lifter that lifts large containers with a maximum load of 24 tons and 20 feet, 20 feet or more from above with a mechanism called a spreader to perform cargo handling. In the past, the management method of the many containers in the station was to insert a piece of paper with arrival station, train number, etc. Written on it into the container slip insert, and the operator looked at it and did the cargo handling work. Containers often went missing. Therefore, the trace system was introduced with the aim of improving the sophistication of container management. By holding the container, the forklift driver automatically checks the destination displayed on the in-vehicle computer screen and performs cargo handling work. Although, when a truck arrives at the station to pick up and deliver containers, work instructions for that truck are automatically displayed. On the screen of the in-vehicle computer inside the forklift, various information necessary for cargo handling work is displayed. The containers can be displayed on a map of the station and can be color-coded for each loaded train. Once you have a container in a forklift, you will automatically see where the container is going and the delivery schedule. These instructions are made by reading RFID tags attached to all containers container wagons and trucks with a forklift-mounted reader. In addition, the GPS antenna mounted on the forklift truck can record and check where the container is placed in the station. We are currently improving the trace system, which has been in operation since 2005. Each forklift has a GPS unit and will log the position of every container it handles. Current problem is that GPS measurements may contain some distance error. The update state will allow each container to have a specific location more accurately, thus improving the safety of truck drivers and leading to more effective operation for forklift operators. This is because truck drivers rarely get off the truck to find the container to find out where it is. We have developed and started operating an application to be installed on the smartphone of a truck driver. It contains 4 features. One is being able to register when you are going to the station to collect or to ship a container. Second is notification of train operation and any news of expected delay. Third is the search function, able to locate a specific container inside the station. Last is a notification from the station operator. So, by using the app, the station gets an advanced information about when the trucks will come, and the truck operators are able to get a heads-up notification. By exchanging information in both directions between truck drivers and freight stations, the necessary waiting time the unnecessary waiting time will be reduced. We are looking into stricter system for container location management. Currently, the exact location of the container unloading is left to the discretion of the individual forklift operator. But the information to be determined is diverse and could be made more efficient operation. The important point is that the location of the containers and the order of work are now decided by the operator. The efficiency of lift work is strongly dependent on the experience of the workers. For example, this train number 1 has 4 cars. First 3 cars goes to destination A station. Currently, when you have a container for A station, you can load it anywhere in the 3 cars, 15 locations. So the evaluation value is the sum container transfer distance and frequency of lock adjustment and gather specific containers. And minimizing this value may lead to an effective position management. This is a result of our proposed method. We simulated the loading position of the container so that the three metrics would be smaller. This is a comparison between recorded data from train number 4097 and our simulation. The loads show each freight car 1 to 20, and column show each loading position within the cars. The color and number are separate information. In the case of this train, the total transfer distance of container in the station was reduced from 21 km to 18 km, and the manual lock adjustment was reduced from 12 times to 4 times. So, by using the proposed method, we may be able to support the operator as well as improve operation at the same time. So next, I would like to talk about the handbrake detection system. The handbrake is a device installed in all wagons that mechanically applies the brakes to the wheels by turning the steering wheel with a human hand. In the past, as a result of traveling less than 100 km of a freight car with the handbrakes tightened, there was an accident in which the wheels deformed and derailed. In the worst case, many people could have died. In the case of this accident, miraculously, no one was killed or injured. Next, I will introduce the measures taken so far. Because hardware countermeasures are challenging to implement, we decided as follows. When station employees would tighten the handbrake, they take a reflective tape from this designated storage and wrap a reflective tape around the handbrake of the container cars, which is tightened handbrakes. However, because these measures are human-based, an inherent risk of human error exists. I will discuss the handbrake detection system to solve these problems. Here, I will introduce an overview of the handbrake detection system. There are three main concepts. The first is to develop a device that directly detects the operating state of the handbrake. The second, to link the operating status of the handbrake with the in-house system. Third, to notify station employees and drivers of handbrake operating status information. The figure shows a schematic of the entire system. We developed a new device that directly detects the operating state of the handbrake. The current problem is that the freight cars don't have an electric power supply. So the system aggregates information from the device in a server using Japan Mobile Carriers KDDI Corporation's Low Power Wide Area (LPWA) communication service. And then it notifies station employees and drivers. This is the handbrake detector we developed. The overall dimensions are small. Length is 113 mm, width is 78 mm, and height is 80 mm. It is light and weighs only 650 grams, and it costs inexpensive. The device monitors the tension of the spring attached to the manual brakes, using a load cell judging the state of the brakes. The state of each freight car is sent to the locomotive driver as well as the station office via a cloud server. Next, I will describe the installation of the handbrake detector on container cars. There are four interesting points when installing the handbrake detector on the container car. Firstly, no large-scale remodeling is required when installing the system on the container car. Secondly, the penetrated return spring pull rod prevents from falling itself. Thirdly, easy to replace in case of failure. Fourthly, battery life can be continuously used for 5 years and can fit the overhaul cycle of the container car. The photographs below show before and after installation on container cars. Using the container car body, the return spring pull rod is passed through the center of the device, and the device is fixed with nuts. The installation of the system is very simple. We are now retrofitting every freight car with this device. After the intro, sorry. Fourth, I would like to introduce remote monitoring system. The photo shows an EH800 type electric locomotive equipped with this system. We have started installation of a remote monitoring device for our class EH800 mainline locomotives. The device is able to monitor two types, one for real-time monitoring and another for later analysis. Real-time monitoring is mainly used at our operating center on the ground and is able to view the same information as the driver monitor on the locomotives. Event monitoring is for later analyzing an event of an error, able to look at the continuous state of a specific system. The log data is stored for further analysis, which may lead to preventive maintenance and realization of condition-based maintenance (CBM). Currently, 20 devices have been installed and monitored. Finally, I would like to talk about the realization of smart freight stations. In Japan, the rapidly declining birth rate and aging population have become serious problems. The working age population of 15 to 64 years old was 66 million in 2016, but it will be 39 million in 2065, a decrease of about 40% compared to 2016. If this situation continues, young people will seek more attractive jobs, so freight station operations that work in a harsh environment outdoors at all times will be shunned. Our greatest sense of crisis is that we will not be able to secure the necessary labor force. Our challenge never ends. Future concepts shown in 2030 long-term vision, which includes operation center which looks over automated transshipment facilities, remote operation of shunting locomotives, unmanned forklifts and AGVs. We will take one step at a time towards the realization of this goal. JR Freight will continue to change as strong and supple as I am. Thank you for your attention. That's all.
Thank you very much, Mr. Otsubo, for coming to share your experience and knowledge with us. We do have time to take in a couple of questions. Does anyone from the audience have question, or you can just press the mic and speak, or you can send it on the chat box if you like. Can I have my question first? I see that the technology that you have been presenting, a lot of them you already implemented. That's correct, isn't it? Yes, I see one of
Yes.
yeah, I see that one of them on the freight operation that you can reduce the manual labor by 20%. When you see the population graph of Japan, what would be the next target? Do you have to carry on reducing the labor further to fit with the population graph? Say in the next 10 years, do you have a target?
So for the answer, Mr. Nakasone, please.
Hi, this is Nakasone. I'm a co-worker of Mr. Otsubo, and I'm currently working on the container handling efficiency. So I'd like to answer your question. So your question was that what's the target, next target?
Say 10 years.
Yes, thank you. Thank you for the question. So as you know, that Japanese population is declining by quite a lot, and our target is to automate the freight handling inside the stations. So currently, we are just trying to cut the frequency of manual labor, but our future goal is to automate and make it so that you don't need the manual labor. But because our company is quite old and equipment has been used for like 10 to 20 years and it hasn't changed. So we need to change the equipment so that it doesn't need manual labor to change the state, or so it can automatically change the state or something like that. I hope this is, were there any points for the question?
Yeah, that's I understand what you mean. That in fact, a lot of the manual labor should disappear really, and that's problem with every country.
Yeah, I hope so.
Yeah, personnel shortage. So thank you very much for sorry, I didn't quite catch your name, Mr. Naka.
Oh, sorry, my name is Nakasone.
Mr. Nakasome and Mr. Otsubo for sharing with us today. Okay, thank you.
Thank you for the question.
Thank you very much.
Well, we're moving on to our next speaker.
มีคำถามหนึ่งครับ
Oh, sorry, that's a question. I was too quick, sorry. Yes.
I would like to know when you set up the new strategy to operate the train freight railway operation, how you set up the priority between freight train and passenger train. It mean like you share track between a freight train and passenger train.
Mr. Nakasone, you can you answer?
Sorry, so your question was that can we change the what from the freight train on freight train and passenger train? Sorry, can you repeat your question again?
It mean like in your railway operation, you share track between a freight train and passenger train.
Yes, exactly. So we used to be one single national railways, but then we split into regional for the people and for the freight train. We only operate freight trains, and the infrastructure is managed by each JR company. So they are for the people to move. So mainly, we only operate in the nighttime or between daytime between the commuter trains. So your question was that can we change the what? Can you give me your question again?
It's been like when you set up the like the scheduling for freight train and passenger train, if train is coming straight in the same time, how you set up the priority?
Oh, so we優先度とかやらないですよね、私たちその
中曽根さん、すみません。
はい
バンコクから島です。多分プライオリティがどのようについているかを質問されているので、例え
はい
ば朝の通勤時間帯が優先だけど、その後に貨物列車と特急列車が同じ優先順位で走らせられますっていうお返事をすればよいのかと思います。すみません、ちょっと私が英語で答えられなくて。
はい。So we can't change the priority at this current time. The priority is up to each customer train. So we don't have priority for the freight trains. I hope that was the answer. So sorry for my English.
It's okay.
Does that answer your question? Okay, that was great. Thank you very much.
Sorry, thank you.
Thank you.
Thank
So,
you.
if you for further discussion, you can of course discuss on the chat box, or we can send you email later. Thank you. Now, moving on to the next paper. The next paper is by Dr. Guoqing Jing, and I'm not sure if I pronounce your name correctly here, but Dr. Jing is a professor in School of Civil Engineering in Beijing Jiaotong University in China. So over the past decade, he has been devoted to the research of engineering and track maintenance work. He has presided over 3 NSFC projects, published more than 50 papers on ballasted track bed, obtained 15 patents, and he published monograph on railway ballasted track bed, lateral resistance of track bed and railway sleepers. And today, he will come to share with us a paper entitled Robot and Drone Inspection in Railway Application and Challenge. So please, Dr. Jing. Hello. Dr. Jing. Okay, we are trying to contact Dr. Jing. So let's give us a minute. Okay. We cannot contact Dr. Jing right now, so we're gonna skip to our next presentation, and meanwhile we'll try to contact him to see if we can connect to China. So our next speaker is Dr. Vanida Pongsaksawat. Dr. Vanida Pongsaksawat from National Science and Technology Development Agency in Thailand. Dr. Pongsaksawat is a senior researcher under Smart Manufacturing and Maintenance Technologies Research Team under Rail and Modern Transport Research Center in NASDA. She has been working for 15 years in corrosion research, and she has been involved in sensor-based corrosion monitoring in field exposure tests in manufacturing plant and a coastal railway line. Now, her team constructed a chloride distribution map, and it is the first Thailand corrosion map on a web-based platform. So today she will be sharing with us her paper entitled Corrosion Monitoring of Railway Components by Atmospheric Corrosion Monitoring or ACM sensor and Electrical Resistance Sensor for Corrosion Rate Prediction. So please welcome Dr. Vanida Pongsaksawat. You forgot to put your mic on. Speak on. Okay.
Thank you very much, Dr. Panadda, for the introduction. And good afternoon, everyone. It's a great opportunity for our research group, RMT, and to join this and to organize this symposium and learn from top experts in this railway technology field. We would also like to take this chance to present our recent work on the corrosion monitoring of railway components by atmospheric corrosion monitoring sensor, we call ACM sensor, and electrical resistance sensor for corrosion rate prediction. These sensors are common type of corrosion monitoring sensor used for steel structure, and we apply it to an onboard train, which is a line run in Thailand, in order to observe the corrosion behavior on the coastal railway line. So the outline of the talk today is actually going to be based on the result from this study, which we going to focus on the ACM sensor output, the ER sensor output, and how they are related to the corrosion behavior. First, I would like to introduce our Rail and Modern Transport Research Center, or RMT. It has been established in 2019, so we are only 3 years. We conduct a research work in collaboration with several parties domestically and internationally to advance the technology in rail and modern transport sector. And Dr. Ekarat is the current director of RMT. RMT is divided into 2 research teams. The first one is Smart Manufacturing and Maintenance Technology. Another one is Intelligent Technology for Mobility. They are formed based on the background of our team, which consists of failure analysis engineer, corrosion, laser welding technology, thermal spray coating, computational, and robotic engineers. So we have been doing some research work related to these topics. And why does Thailand has to develop the railway industry? If you look at this railway network map of every countries around the world, we can observe that dense railway network are centered at the world economic leader countries. And because railway is the most efficient mean of transportation and it is also the most sustainable, and we agree that all the technical development should goes in that direction in the future. And the status of Thailand railway network is in this circle here. In the Southeast Asia, we still have a lot of opportunity to expand and connect the railway network domestically and through the neighboring countries. And that will open a lot more opportunity in terms of economics and growth. Let's start with the railway network map in Bangkok. About 20 years ago, Bangkok had the first electric train running on an elevated track we call BTS. And a few years later, we have an underground service train start to operate. Both of these lines only provide service within narrow region in the center of Bangkok. And since then, especially the past 10 years, the train network has expanded to reach more area around Bangkok. And it's a good sign for Bangkok people and also the tourists who visit Thailand and Bangkok to see this happen. And we also have a bigger plan in the future. For the railway network that goes across the country, the railway is operated by the State Railway of Thailand. The major lines go through the major city around the country in 6 regions. The upper part is the inland services, and the lower part is the coastal line services. Because the southern part of Thailand is like a peninsula, one side is facing the Gulf of Thailand and the other side is facing the Andaman Sea. We see long train track across the bottom part of the country that is considered marine environment. For the next 15 years, Thailand actually has plans to upgrade some single track to double track in the major lines. We are also expecting to take the high-speed railway technology for each region, and that is the plan that is already going on, especially the 3 airport high-speed train, which connects the airport between Bangkok, Samut Prakan, and Chonburi. So maybe next time you visit Thailand, you can get off the plane, take the high-speed train to Pattaya. So as I mentioned that the marine environment cover mostly of the southern part of Thailand, and sea salt or coral is the most influencing factor that cause corrosion on metal. So our team take a case study of the coastal line example. We chose Ban Lam Mae Krong line, which is a short train from these 2 stations, and it's only 33 kilometers one way. The train travel on this track. They are fixed route train, so it's going back and forth 4 trips per day. We can see the picture here is the train goes past through the Mae Krong railway market. The train is actually a 40 years old train made in Japan. It's a NKF type diesel engine. The maximum speed of this model is 120 km per hour, but the service speed is only not more than 55 km per hour. And because it is located 2 kilometers from the sea, so we are interested in the corrosion of the structural steel of the train. We have visited the depot in Bangkok and observed the train that came in for major maintenance, and we see that steel structure have very severe corrosion, especially the coated steel will have degraded paint, especially at the water leak place. Another location with severe corrosion is the underfloor area. We observe coating failure, and usually this can came in for major maintenance every 6 years. But in fact, the coating might fail before that time interval. So we apply the corrosion monitoring sensor at different locations on the rolling stock, the roof, the interior part, the exterior part, and the underfloor. We also install the sample coupon in order to monitor the actual corrosion loss, along with the speedometer to collect GPS data and speed. So with this type of sensor, the corrosion monitoring sensor, we hope to predict how severe the corrosion is for different part of the train. This slide shows the type of sensor we use and how we conduct the test. The ACM sensor is for measuring the atmospheric corrosion. It's a galvanic type sensor, which means that the electrodes are made of different materials. The substrate is carbon steel, and the top surface electrode is silver. So when these two materials are exposed to rain or condensation, and there is a water film on top, there will be galvanic corrosion going on, and we can detect the amount of corrosion through the current output. When the sensor are wet, the current output are in the range above 0.01 microampere. And when the surface is dry, the current will be below that current range. So this type of sensor we have to replace every month or in every 1 or 2 months, because they're gonna corrode and use up. But we can monitor the current output in form of galvanic current. The next sensor is called air core. This is a commercialized name. It detect the corrosion based on electrical resistance of the rust layer and convert that to thickness loss. This type of sensor can be used for long term, so we can expose it for 12 months, and it has built-in data logger. The speedometer, we select the general speedometer to collect GPS location and speed of the train. For the coupon, we select the materials that made for railway components and some of the more corrosion resistant type, and we monitor the weight loss or the change in corrosion every 3 months, 6 months, and 12 months. Out of the three sensors, only the ACM sensor that we can modify to transmit data through the wireless cloud. So from the data logger of ACM sensor, we connect it to Raspberry Pi. Then we connect that with the GSM module, which we can put the SIM card to have the internet access. So with that, we wrote some script in order to construct the data logger to transmit data to cloud database. So we can obtain the data online and analyze to calculate the cumulative charge, which is directly related to the corrosion rate, the time of wetness, the current output, and we can sort the data based on the speed. So this slide shows the work that we did in the installation of sensor and sample on this Ban Lam Mae Krong train. The roof station, the sample were mounted on a platform and secure at the ventilation hole. For the interior structure, here there's a gap between inner panel and outer panel where the window will be slide off if there is no rain. But after rain, the window will also be opened and placed in between this gap. So it creates a moist area. So that's one of the test location that we install the sample and the sensor. For underfloor area, we secure the sample and sensor underneath the stairs. The normal operating hour for this train is from 6 a.m. to 6 p.m. And we start the test in August 2020. During the first 5 months, the train operated normally 4 round trips per day. But after that, in January 2021, the train had to stop the service for 3 months due to COVID pandemic. And the service was resumed in April, but only operated for 50%. So the data show here will be only valid for this time schedule. Next, we're gonna take a look at the output from the sensor and see how they are related to corrosion. This slide shows the output from the ACM sensor that we analyzed. The polar plot on the left-hand side shows the current output throughout the year, throughout 1 year. The scale on this shows the log scale of the current. Red means wet and blue means dry. Anything in the middle means the borderline between wet and dry. So we can quickly observe that on the roof, usually the wet time will be very short, followed by mostly a dry time. But for the underfloor area, we observe prolonged wet time, especially in the rainy season. So if we look at the plot in the middle on the XY axis, is the cumulative wet and dry time each month. And we observe that the roof is dominated by dry period and the underfloor is dominated by wet period for half a year and then dry period for the other half of the year. So that depends on the weather. Finally, we calculate the cumulative charge and cumulative time of wetness. So we obtain the result that the roof has the highest cumulative charge, which is an indication of high chloride deposition rate, followed by the underfloor area and interior part. But for total time of wetness, the underfloor area has the highest time of wetness, which is due to it always has water film on the sensor because there is no access to sun under that area. The coupon samples that we obtain from different sections of the the train body are shown here. We observe increased rust coverage as the exposure time increased for the interior samples. For underfloor and roof sample, the rust cover pretty much 100% of the exposed area since the first 3 months, and it seemed to build up when the exposure time increased. There is also a buildup of dust from these underfloor and roof top. If we remove the rust and take the different amount of weight, we can plot the weight loss over time as shown here. The weight loss is increased with time, with the exposure time, and it is the highest for the roof sample. If we categorize this corrosivity, it is ranked as C3 level based on ISO standard. For the underfloor and interior part, the corrosivity were lower in the C2 range. We also plot cumulative charge at different locations, the current we read out from the ACM sensor over time. we observe a similar trend with the weight loss. So that means we can actually correlate the weight loss and the cumulative charge as shown on the bottom plots. The interior and underfloor area follow one equation, but the roof is more aggressive, so it has another separate equation. This plot shows that the ACM sensor can be used to predict the corrosion rate of carbon steel. Next, for the air core sensor, we monitor in the interior structure. So it calculates it. The output is corrosion loss in the unit of micron over time. The blue line on this curve shows the change in thickness loss of the sample, and we can observe a very detailed change each month. But after around 1 year of exposure test, we observe a big jump of data here, and it turned out that the air core sensor got damaged, so we stopped the test at 1 year. But only from the 1 year data, when we compare to the sample coupons, that we remove the rust and calculate weight loss and convert it to thickness loss, we see quite a good agreement in terms of weight change, thickness change. So it means that the air core sensor can be applied to predict the corrosion rate of carbon steel as well on the train. On the final point, we would like to know the effect of the train speed and corrosion. Each month, we have this set of data of ACM current output and the speed. We can plot all the data together, and so far we observe no specific pattern of current output and the train speed. However, we observe some current response after rain that is affected by time, speed, and location. For example, this plot shows the current on the roof as blue line, the underfloor as orange line, and the speed as black line. When the roof current is above 1 microampere, it means it rains. If the rain occurs during daytime, we notice that the roof takes quicker time to dry, which may be caused by the sunshine or the movement of the train that make it dry quicker. But for the underfloor area, rain during daytime takes longer to dry. So that's one observation. Another one is when it rains in the evening or after the operating hour, sometimes it takes longer to dry also for the roof. So there are a lot of information on this type of data, and we need more time to analyze them, or actually need a better way to analyze them. So another information we obtain from this speed and charge is the ratio of the charge read out during runtime and stop time. So this plot shows the percentage of wet time during running and stopping time. We got 6 month data for wet season and 1 month data for dry season. And we noticed that most of the charge we read out are from the stopping time. One reason may be because the stopping time is longer, but it's also that the stopping time is at night, which has high relative humidity as well. So in order to control the corrosion, we have to take into account both operating hours and off-service operating hours. So in conclusion, the study shows that the corrosion at the roof is the most corrosive, and the time of wetness under the floor is the longest, especially during the rainy season. We can apply the ACM sensor and air core sensor to monitor the corrosion. And from the result of this work, it might not be directly applicable to the high-speed train because there's an evidence that when the vehicle travels above 70 km per hour, the charge from the underfloor area could be higher than the roof. So it's another risk of the high-speed train that might have more severe corrosion. And we can apply the ACM sensor and other corrosion monitoring sensor for the onboard train in order to predict the corrosion more accurately in the future. And finally, I would like to give all the credit to my team who carry out excellent work, the funding from NASDA and the permission to conduct the onboard test from SRT. Thank you very much.
Thank you very much, Dr. Vanida, for the interesting presentation. Now we got time for one quick question. If anyone from the audience have a question, you can speak. Otherwise, I'd like to ask a question. So you have done an experiment on a short section of a railway, right? Is there any way to extrapolate that corrosion rate or the result that you have found throughout Thailand as a nationwide? Yeah.
Okay. Currently, the information we have is the train that runs in the southern part of Thailand. They're not on the fixed route. Sometimes they are rotated to run in a different section of the country. But if we would like to know the actual service of particular train without concerning about particular environment, we can use this approach to monitor the corrosion overall. But in this study, we actually aim for the coastal line first because we will see the obvious effect of the chloride sea salt on corrosion.
But we still need to install the sensor to observe.
Yes.
Those lines still. Okay.
For the new environment, we need to repeat the experiment.
Okay. Right. Thank you very much. Thank you, Dr. Vanida. We'll move on. We're going to move back, in fact, to Professor Jing. Dr. Jing, are you with us?
Yes, I'm with you now.
Okay, let me announce you in anyway. I did once already, but let's do it again. So next we have Dr. Guo Qing Jing. Dr. Jing is a professor in the School of Civil Engineering in Beijing, Jiangtao University, China. Over the past decade, he has been devoted to the track engineering and track maintenance work. He has presided over 3 NSFC projects, published more than 50 papers on ballasted track bed. He obtained 15 patents, published monograph on railway ballasted track bed, lateral resistance on track bed, and railway sleepers. And today he will be giving us a presentation on robot and drone inspection in railway, application and challenge. Please, Dr. Jing.
Thanks for the introduction, and I'm honored to be invited to make the presentation. In fact, I have many friends from Thailand, like Professor Saik of Birmingham, and Professor Tops Pirung from CMU, as well as newly friend of Kung from the capital. Today, my presentation is the robots, which we are working on. We have 2 projects about railway inspection by robots, as well as railway inspection by drones in desert railway lines. And this is my very short introduction. In the past, I'm working on track evaluation, and now we have GPR and real ultrasonic detector. We are working with AI method, and I'm trying to have like a company in Thailand, because Thailand will booming to have more infrastructure of railway, and that's why I'd like to have more friends from Thailand. The second one is I'm working on like a smart and sustainable railway. Smart, which is intelligence, like the advanced method as well, equipment, and sustainable, which means low carbon, like green materials in railway engineering. The third one is I'm have lots of collaborations in railway companies. Just for example, most of my research and equipment I from these two companies. One is South Survey, which is with lots of location marine railway equipment, as well as the second one is a robot railway company in Shenzhen. These two companies are in the share market. The left side is my WeChat. Now this is my content of the presentation. First, I would like to make an introduction about the China railway system. For example, like 70 years ago, we just have 21,000 railway kilometers. But now we have more than 140 kilometers of railway. As well as we have the speed. For example, like from the beginning of China Republic of China, the speed is less than 80 kilometers per hour. And our first railway line, high-speed railway line, is like Guangzhou-Shenzhen high-speed railway lines. We rent the car trains from other countries. The next one is I want to make a note and to Thailand people. Before we have the high-speed railway system, in fact, we made 6 rounds of speed up, like improvement of existing railway infrastructures. And after the 6th round of speed up, more than 8,000 kilometers of railway, existing railway, put into operation with speed above 200 kilometers per hour. So before 2008, in fact, we had the high-speed railway system by the definition of UIC, not only the newly built. For example, 2008, for the Olympic Games, we built the first newly built railway, high-speed railway, which is speed is 350 kilometers per hour. For the moment, in China, we have 2 railway lines operated at the maximum speed is 350 kilometers per hour. And now China is working on for the 400 kilometer of per hour railway system with operating speed. Another thing is inspection technology. In the past, we use static, and like 20 years ago, 30 years ago, we use both static and dynamic evaluation method. Now, we have a center we call infrastructure evaluation center. This center is responsible for all the China high-speed railway dynamic inspection. And the China Railway Company pays this company by each kilometer of dynamic inspection. They have 10 high-speed inspection trains, TRV trains. Inspection technology for the past, we use the static track geometry inspection, like the gauge, electric gauge, trolley with total station. But now we prefer to use more dynamic solutions. For the inspection technology, the traditional inspection, we call it 4DS, which is dangerous, difficult, dirty, and boring. For example, now in China, we have more than 800,000 employees of railway technicians, workers. These kind of jobs are boring and dangerous and repetitive, and most of the work carried out at night, very bad for the health of the worker. Another thing is I want to make a very quick introduction of dynamic track geometry detection in China. This is development, and we import the real inspection vehicles, and now we have the high speed. For example, 1 month ago we export China high speed inspection trains to Indonesia for the future operation high speed railway line. Each high speed railway lines will have the high speed TRV, the same velocity. This is TRV. High speed TRV. We have this one, we have this, we call this yellow doctor, where the speed is 300, more than 300 km per hour, with the same speed of the operation. We have 10 high speed TRV. Just my neighbor, it is like 500 meters from my office now. This is track status evaluation, like TQI, like the generally we use the method, and then we add the car body acceleration. We use the TKI. We use dynamic evaluation just gradually from 1 to 5. This is both the dynamic and the static evaluation method. And track inspection, like 20 years ago, mostly we use manual inspection. And now we prefer to use more like artificial intelligence. We used all the cameras, photos, laser to get the information from the track on the train. We mostly use like artificial intelligence method to analyze this track dynamic of the China railway system inspection. And this maintenance strategy, which is like the law of the maintenance for the past, for like early days of after accident, we make the maintenance. And now we, and like 40 years ago, 40, 60 years ago, we use periodic repair, which every half year, every 1 year, every 2 years for the maintenance. And now we, and like 15 years ago, we use concentrated repair, quality-oriented repair, based on the operation, the track quality, we make the repair plans. Now we prefer use like a predictive operation based on the analysis reports of track geometry. This China. The second part is like problems and challenges. Why we do the research? Why there are many companies into this industry? You know, China, we have like a lot of challenge in like labor cost as well as shortage. China, right now we have less newborn babies than ever. Like in the future, more people will get older and retired, but less young people. For example, more people, and another thing is more people are willing to working as a deliveryman, because drive a motor on the street quick, and each month the salary is more than 10,000 RMB. Like some people can make like 20,000 RMB, which is a huge loss of money compared with the traditional railway workers, which are dangerous and cold, sometimes very cold in winter, especially in north of China, wind and boring and lonely. So that's why the railway company try to reduce the cost of operation as well as maintenance. We reduce labor, and we want to make fast, accurate analysis, because, for example, for the ultrasonic rail detection, even after the work, we have need another half of people to make the analysis, to read, to watch the pictures each by each. But no, we developed the robot. For another one, in fact, we classified UAV as some kind of robot. This is one of my robot drone project carried out. It is working now in Inner Mongolia, the railway, with lots of drift of the sand, desert. We are working now, use the Linda, and as well as the photo to measure, to locate the drift, as well as mitigation of the sand. With the accuracy is 5 millimeter, with 3D point cloud format. We can not only the sand, but also the track profile, as well as OCS. This is the working we are working now. It will ended at end of this year. China has more than 10,000 kilometers of railway in desert. This is one of our inspection robots. We published one paper as a review paper. I hope if you're interested in, you can download this. Lots of like ideas, classifications about the review robot. This is some like a development of other countries, like Italy, EU. This is like a research product. This is from America. RealPad, this is very big one, and also these two companies from China. This is Shenhao. I'm working as a senior consultant for this company, and they give me two railway robot research projects. Each one is like 1 million RMB, 1 million RMB. We make testing for the compare with the railway traditional method. This is Jingdong inspection robot located in Beijing. This is a very big company. They have a branch one to use robots for the railway system. This is our test. My student testing at night. We put it on the track. This is on the track, automatically for detection, and automatically come back to the initial position or where you want it be. This is like the real profile, like the fastening, ballast bed. This is testing in Beijing. And this company also has the vehicle inspection robot under the vehicle, the bottom, to check the bolts, the position, and this is the roof inspection robot to make cleaning of the roof, especially for the OCS, the electricity part. And another team in China in civil engineering school, they make the research like a bridge inspection robot. This is classification like UAV, like view, snake, and underwater as well. For example, this is one of my colleagues in civil engineering of bridge engineering department. They use the robot for detection of the like corruption of the piers after years of operation. And this is this is one photo video. In fact, this is because of China lack of the water, loss of the bridge, the piers out of the water. We can find out there is like a total damage. The past method uses dialman to detection. This is the photo from pier damage. We use the sonar for the video, like detection, inspection of the. Another thing is bridge inspection in other countries, like Canada, like France. These pictures. I share this presentation with the conference organizer. You can ask him or me to share this copy of my slides. Another one is in China, we have many companies and universities developed the tidal inspection robot. This is from Hamburg, the world famous company in marine system, and this is the EU robot product. And this is one thing I present. This is from Netherlands. My idea in the future is use this 4 feet robot. It's very cheap, and is about 20,000 RMB, and it can run on the ballast, run off the ballast. This is more flexible than the on-track robot, and this can replace the man of working. In the future, it's like the drone. Firstly, as detective, and then future maybe some simple operation like coating, like oil, like fastener working. This is like a category inspection and working robot from Japan, and this is like the link, and they are working on it in the future because Japan is also a country with less young people working in railway engineering. They use VR and robot like a Gerda, a soldier. This is a company I'm working with, railway ultrasonic, a real ultrasonic company. They have we call it two wheels and two tracks, two reels. It can detect two tracks. This is more flexible and more fast than the common walking speed. This is just 5 km/h for one reel, but this can run at 20 km/h with two reels. We are working on this one and developed the AI classification system to replace the laboring work of real problem detection. This one is on the rails. Is very expensive. Speed is very fast. High speed, low speed, and walking speed. This is some of our working research, like our publications, like the classification based on the ultrasonic data. This is track side inspection. It also kind of robot, if you like, a laser. This is my future ideas. This is kind of like from the spatial and set we use the INSA, and for structural deformation we use the DIC, and this on-track system. This is for Raleigh from Netherlands. This is more economical than the traditional on train system. On train system is very expensive, but this one is flexible to take off with 2 minutes, within 2 minutes, and loaded with 2 minutes. And this track bad GPR. We have a GPR, and I want to set up like a GPR company in Thailand to collaborate with professor like Tops Pierpont. And this is track inspection robot we are working on. I think this is in the future is like a system. This is GPR. This sorry, it is in Chinese. This is our publications. This is a publication. We use GPR like 4 years working totally. We do the test, calibration, even like separation of the folding materials. We are working. We collaborate with cars for rather in the future. Inside is very good solution and to collaborate with railway robot as well. Another thing I want to introduce about Rela. Rela is, as I mentioned before, this Netherlands system, and they are very flexible. They can put on the train easily and take off easily, and with like IMU, like with the antenna, with like a LiDAR system, and it totally dynamic evaluation, but cheaper than the EM set. This system, this example. And another thing is my working. We publication with smart. One of my PhD, he will graduate very soon. Muhammad Sehakuli, and his PhD topic is smart railway sleepers. We use like nanotubes. We use like CNTS and carbon nanotubes for railway sleeper, and we also use like piezo electronic for the capturing the energy by the train with the train passing by. This is a smart railway sleeper. IoT, some kind of IoT things. I changed the traditional sleeper into IoT of things, IoT, to make the track smart. Another research is smart sleeper, smart ballast. This is a work carried by Dr. Huang Hai, and this is work carried out by my side. Like this is publication, like prediction ballast fragmentation by machine learning method, and use topology for the calibration of ballast before and after the use this smart sleeper ballast. This smart railway worker, I'm working with a company of South Survey. We put this, we call it smart railway worker to put the smart sensors like the Linda, like the camera sensors to record this for you mainly used for the railway infrastructure asset management. We are working on the railway management system. In the future, my solution is like for the intelligence inspection and maintenance, robot, UAV, satellite, and plus AI. And for China, we have lots of railway data. We have numerous data, but we have too much data. We could not find out key factors. We are working on to use artificial intelligence technology to improve of the railway diagnosis and for the future predictive maintenance. My team, like now we have 3 people working on big data analysis, like ultrasonic and GPR plus AI. We have software now. We're working on it. We want to make it into a company in the future to collaborate with the investigator. Another thing we want to in the future, I think it will be great to set up like decision-making expert system because railway engineering and with lots of knowledge and borrowing, we want to reduce the cost or the time of study for becoming a railway expert especially for the working level on site. This is my research. Thanks. This is my presentation, and hope to have collaborations. Any questions? If you
Thank you. Thank you, Dr. Jing, for a very informative presentation. We have time for 1 or 2 questions. Does anyone from the audience have any question? Can I get mine in first? Dr. Jing, I was wondering if we want to look to inspect something in a smaller scale, like not just a geometry. If we want to crack or defect on the surface of the railway, what system currently have the fastest speed? Is it possible in things like in vehicle system to detect defects on the railway, on the rail?
Okay, this is very, thank you for the question. This is very, how to say, interesting question. And in fact, based on our experience, it's not simple, or it is too simple to judge which one is best, which one is fast. In fact, for example, for the rail detection, we use both ultrasonic. Now we are working use magnetic method because ultrasonic is very for the inner side cracks, but the magnetic method can detect the micro cracks of the surface. So sometimes we don't. It's not only one solution. We need several solutions working together. So it's not easily to judge which one is faster, the faster better. But it's not simple. The fast is better, but we also count on the economical level. For when we decide which technique or solution, we should keep it in mind. First is reliability, which is like the accuracy. The second one is like the efficiency. The third one is the economy. Because if it's too expensive, we could not afford it. In the future, reliable, accurate efficiency, and less cost is best solution. So sometimes we need to make a decision based on the situation of your country. Like for example, Thailand is booming with young people, lots of young people, and the infrastructure is increased. So different stage of development. We needed to make a evaluation of the technique based on the local situation. Thank you.
Thank you. Right. Thank you for that. Now if you have any more questions, please send it on the chat line.
Thank you.
We to a break now. Thank you very much, Dr. Jing. We're coming up to a break. We're going to have 15-minute break and we'll come back 14:45 and see you then. Thank you.
Thank you.
Okay. Welcome back everyone to the second half of the afternoon session of our special symposium. This the last now we have 3 papers left, and the first paper will be presented by Dr. Pirapong Jitsangiem. Dr. Pirapong is an associate professor and the director of the Advanced Railway Civil and Foundation Engineering Center at Chiang Mai University. His research interests include advanced road pavement materials, transportation geotechniques, and waste utilization in road construction. And he has published more than 100 research papers in peer-reviewed national and international journals and conferences. Now, today he will be giving us a presentation entitled Development of a Single Measurement Device Unit for Monitoring Railway Ballast Behavior. So please, Dr. Pirapong.
Hello, thank you, the chairperson, for introducing my a bit of the bio about my backgrounds. Actually, I would like to thank the organizer first of all before jumping to my presentations today. I would like to thank MTech and Nesta for inviting me to this event. Actually, at first, when Dr. Ekarat invited me to this event, when I have a look about the title of the event about the mega trends in the future mobility, I'm quite have a bit of the hesitations to join because my area is about the civil engineering. It's quite the low tech. Actually, eventually I can come up with some topic that can show you all today on the topics of the development of the single measurements unit device unit for monitoring railways ballast behavior. Actually, I'm a close friend with Professor Cao Jing from Paching Chiaotong, the previous presenter of this one. He showed a lot, about the advancement, how to capture all the behavior of the track structure. I think this kind of thing would be less intentions in Thailand. And I think that Nesta is the leading organizations for to be a part of the Thailand railway development. Should be aware about this thing, the trend's gonna be coming. Okay, for my presentation today, actually, because the topic is about how to measure the behavior of the ballads, that going to be shown on the slide here. The presentations outline. I would start the introductions and my motivations on this one, including the objectives, methodology, result, and end up with the conclusions. And I would like to spend a few minutes here to present. Now I'm working in the Chiang Mai University, the biggest local university in Thailand, located in the up north of the country. I think the Chiang Mai would be well known for everyone, for the tourist province, and everyone want to visit Chiang Mai and to see how beautiful it is. And Chiang Mai University located in the Mueang Chiang Mai. And in the past few years, Chiang Mai University tried very hard, to establish something to assist the railway development for our countries. At the end, we can establish the Chiang Mai University Advanced Railway Civil and Foundation Engineering Center, or CMU Rail CFC, with the assistance from the Central South University. And you can see the big loading facilities for the rail, for full-scale tests at the Central South University, how important of the track structure for the railway development. And you can see this show a bit about the center. You can see the clip on the screen. I took this clip myself. You can see the track is still up and down. This is the current situations of the some of the track qualities of Thai railway network. And now we try to talking about the digital twins and all of those things that okay, it's a big words at the moment in the research society, right? But when we have a look about the track qualities on the railway infrastructure, and it's also the extremely important for the development as well. That's why Chiang Mai University the research of the Chiang Mai University try to target on the railway infrastructure, in particular the substructure. That's why we want to focus on the ballast layer, sub-ballast layer, including the subgrade, including the flooding, how this affect to the railway behavior under the train moving conditions. And Chiang Mai University invested some significant budget, to invest the set of the advanced testing facilities to handle the structure research. That means from now on, we got quite the advanced facility to investigate on the real behavior of the substructure based on the Thailand conditions. That's gonna be brief explanations or the brief introductions about my ongoing research in the next few years based on the set of the facilities that we currently have at the Chiang Mai University. Okay, get back to the my presentations topic today. I would like to start with my research motivations. And you can see the picture is my close friend, Associate Professor Xian Yu from the University of South Carolina. We bumped into each other in the China, a few years before the COVID pandemics. We got a chance to discuss a lot about the how to develop the so-called the railroad infrastructure 4.2, and at the end, Professor Xian Yu can publish this topic in the Journal of the Transportation Geotechnique already. And everyone would know that in terms of the industry development for the first, second, and the third, now we going to the eras of the fourth one, which is about the industry 4.2, right? Everyone would ring a bells about the big words of the Thailand 4.2, 4.8, 4.2. What does it mean? That means for this kind of the industry development, that means object can communicate to the object by using the high end of the Internet of Things and cloud computing. For the railroad infrastructure 4.2 as well, that means objects need to communicate to each other, and that means we go into the absolutely new eras for the railroad 4.0. And I would like, because everyone would work in the different sky of the research fields, I would like to introduce you a bit about the railway tracks. Of course, you can see on the left, on the right-hand side, for the picture, and this show the ballast tracks, which is the majority of the tracks of the Thailand railway network. And you can see the component on the left-hand side here. Beneath the steel rails and the sleeper, they have some ballasts and the sub-ballast, including the subgrade layer. And these show the components of the track structure of the ballasted track. And you can see now we're talking about the hybrid computing of the ballast behavior, right? That means how could we understand the behavior of this kind of the structure in real time. That means all the powerful computing method, including the sensor technology, need to come into the pictures. That means Professor Xian Yu show here is quite important about the discrete element simulations, or the DEM. And this one, it's just like the theory of the granular method, how to evaluate the behavior of the isolate particle, and when the particle get together, what gonna look like, what gonna behave. We have to understand that through the discrete element model programs, and at the same time we have to put in the sensor technology, the advanced sensor technology, to capture all the behavior of the materials. And this show the sensing mechanism and real-time computing, smart computing here. For the smart computing, got the two components here about the sensor and DM, right? And at the end, we can predict the based on real-time behavior of the materials or the ballast layer. This kind of thing, I'm really interested on that because my previous research field relating to the pavement technology. On that time, I tried to think how could we capture the real-time behavior of the pavement structure, which is the same story at the railroads as well. And when I discussed with the Professor Chien Yu, we come up with this kind of the concept, and this gonna be the good foundations for the digital twins as well, right? How you can capture everything in the real time, including the railway infrastructure. You can see on the sensor here, we change to be the smart rock. The smart rock, Professor Gao Jing touched on this a bit, Actually, this smart rock sensor developed by Professor Hai Huang from the Penn State University of USA. He's going to be the one. This is my research motivations. Number 2, you can know that when in the way that you're going to measure the real behavior of the rocks, in the ballast layer. Of course, you have to mimic the synthetic rock with the sensor technology in there and put in that layer during the construction and let that thing monitor what's going on in the ballast layer to understand the behavior under the real actions, including the temperature change. And this one is quite fascinate me a lot. And you can see how this kind of the sensor capable of doing something. You can see the movement, the rotations, and everything. It's quite amazing to me that how Professor Hai Huang can develop this thing. And you can see this is the capability of the smart rock, as you can see, and this during the development. Okay, and you can see another one, and you see the smart rock here. Of course, when we got the quite good piece of the sensor device with the similar shape with the ballast rock, right? We can put this one in during the constructions, and then we can know everything what's going on in there when this layer is subjected to the loading and environmental actions. You can see that we can install the synthetic ballast with the sensor technology. Sorry for that. With the sensor technology, and you can see that, and this can communicate, transfer transfer the informations to the cloud base, and then they make the information interpretations, and we know that when we gonna fix this track. That's mean for this kind of the diagrams or the workflow, we can dream for the track that never damage, or we can make the good preventive maintenance scheme on time. Not wait until the structural failure. Okay, get back to the topics. Everyone would know that I did how good of the smart rock, right? And when I get back to Thailand, and I think how can I create this thing in Thailand? That's why I assign one of my master students together with a groups of the bachelor degree student, try to develop the smart unit, single unit based on the Thai version. And this one, I think this one is not complicated or the complex technology, but show the good attempt based on the Thailand knowledge, that we how up to the ceiling of the capability that how we can do that in Thailand at the beginning. And you can see that this show the project pathway. Of course, we're gonna start with we have to learn more informations about the electronic knowledge because all of my research group, we got the civil engineering background, and then we set up the equipments, the methodology, how to put all together, and including the validation scheme and show the result, how we can show the results. And this I'm gonna show you, probably this one is quite simple, but in the another angle, it show that if you want to do something, we can try to start with some simple things. That's why when I discuss with my research team, we start with to select the good sensor. That means we can use the gyro sensor and the flex sensor to be the main sensor to capture how they rotate and about the stress and strain relationships, including the microcontrollers and the circuit boards. And this device, my teams can order that online. It's very easy, and that's why we try to make and go for this model for the accelerometer and the gyro modules, and including the microcontroller as well. This one show the typical microcontrollers that are used to develop this measuring device, including the flex sensor. And this one, you can shop this one online easily. And this show the circuit board that we try to develop, to match up all things together. And for the equipments, on that time, we try to cast the model, what kind gonna be the good model. Of course, we cannot replicate by using the 3D printer to get the rock shape like the smart rock, because that one is quite advanced. Of course, we think that what we try to develop here is the first prototype. That means we did some literature review that to make at the Q shapes, they're going to be the best option in the meantime. That's why we made decision to cast the Q shape like that one show on the screen, including for the show. We design by using the EVA, and for the battery, we use a 9-volt battery, including the mesh circuit resistant and the solder, as shown on the slide. And this show when we try to merge all the electronic equipments, including the sensor, into the prototype. The first one, we try to make arrangement the prototype. The maximum size is 12 by 12 by 12 cubic centimeters. And this one, we try to set up the system, but for the size wise, 15 by 15, it's quite big, it's not matched with the maximum size of the ballard. That's why we try to reduce the circuit board, the size of the circuit board, until up to the end we can make the second prototype that can reduce the size significantly up to 7 by 7 cubic centimeters. And this one is compatible with the max size of the aggregate, because based on the standard of the aggregate, the max size of the aggregate is around 6 to 7 centimeters. That means we can fabricate the model to match with the max size of the ballard rock, and then that's what we dream for. And then this show the methodology that we try to do. We make the cubic mock-up and print the circuit board, right, and put the sensor in together, and we use the Arduino software, with some coding to transfer the electronics informations to be the thing that we can understand. And we think beyond that, how to storage the data and about the data presentations. And they're going to be quite a simple method, as I said, but it showed the good attempt, at least the NESTA would know that some kind of the single measuring device here can be established already in Thailand under my research group. And you can see the picture here show how to put all things together. And this show the gyro, the sensor and everything to get attached with the circuit board and the controller. and then we install everything into the cubic shape like this one and make the connections with the computer based on the wireless method. And of course we use the free source, the Arduino programs with the coding to make sure that the electronic information can transfer well, you know, to the computer. And then we also design the storage data to the cloud by using the Google Sheet, you know. And this one my student did quite well, you know, from my view, based on the simple things. But we try to this and touch on what I want to see, you know, for the first prototype that we try to establish here. And I show you the clips, you know, after we put all in the units and try to shaking a bit to see whether or not the sensor can capture all the things that we want to see after we install the battery into a unit. You can see that, and this the hands of my student, and you can see that when we try to shake it up, you know, they got the quite good communications through the computers, and then the measuring results being recorded in the Google Sheets, and we try to design the interface to capture something that we want to see, of course. And this one is not good as the smart rock, but it can grab the essential informations just in case that we can put these single units during the constructions activities, and then we can capture something occurring in the real tracks, you know. And this one show the clips. You can see all the things show on the screen. This my student try to shake it up, as I said. And this I'm quite proud to the first group that developed something, and this one that means flex sensor and gyro sensor works well, and including the all the coding and the script that we try to set up to capture all the informations in the cloud-based system. Okay, let's go to another one. And then when we know that all the sensor can communicate and collect everything, you know, as informations, we try to make some what is called the validation process, and this one we try to set up the calibrations, the function test, and everything. And as I show you for the calibrations, we try to make the simple this one about the flex sensor. This show the validating arrangement, like we know the load, we try to push in the flex sensor, and we try to capture how deflex they are together with the thing that we can capture from the loading ramps. And these show the gyro sensor. We try to rotate and measuring the angle rotations together with the thing that we can capture from the units, and including the acceleration rate as well. And this show arrangement of the acceleration testing of the unit. And this show the results, you know, for the flex sensor is good correlations with the real measurements to the measuring device, including the rotations of the axis, you know, nothing wrong from the real measurements. And for the acceleration rate is quite well, you know. That's mean the thing that we try to make the separate validations in terms of the flex sensors and the gyro in terms of the angle rotations and accelerations is quite well with the real measurements. And then we test the data transmission and the cloud with the wireless system. And this show you, you know, the methodology and show the result that we capture from the Google Sheet that automatically install, you know, in the cloud system to the Google Drive through the Google Sheet. And this show the example how all the information we have against with the times goes by. And this show another rotations from the gyro. And this, of course, we can put on the diagrams about to make ourselves understand and give them more insight about all the informations, against by the time here. That's going to be the interface that we can develop, for our first single unit. Okay. For my going to the last slide, I got the recommendations as well for the long-term monitoring. We're looking for, I don't know, for the tracks, probably up to 50 years. Of course, the good idea about the instantly install the device during the construction process, right? That's going to be the brilliant idea, but we have to think about how the device can survive, with the long-term battery. Because, and this is just idea, because I put the 9-volt battery in, but for the smart rock as well, somehow the big question have to come up with about the long-term battery. How could you make this measuring device, to be last long as the infrastructure? That can be the next development and the big questions for this kind of thing. Okay, that's gonna be all for my presentations. Thank you for your attention, and hopefully everyone enjoyed with the simple things have been done in Chiang Mai University.
Thank you very much, Dr. Pirapong. That was fascinating how you gonna hide a spy rock in your ballast. We got time for maybe a couple of questions. If anyone from the audience have a question, you can speak now. Okay, may I have a question? Dr. Pirapong, I was wondering, because you were mentioning that the shape of the rock, the first shape that you were looking at was a bit too complicated. What would be the implication of different shape of the rock?
And you can see that if everyone outside the field, right, you would understand that the first stage of the material behavior gonna face with the fresh thing, right? But when the materials been subjected to the cyclic loading conditions and including the environmental factor, the materials start to deteriorate. That means the behavior of the material is not the same as the first day after the constructions. That means the shape of the rock had been changed by when times goes by. That's why, when you think about the material in civil engineering after the post-construction, it cannot be changed day by day. That's why we have to capture the real behavior of the material. That means the shape and everything, the material gonna change when subjected to the external loading conditions. That means this point is very important because everyone would understand that everything gonna be fixed, as the first day after construction. But it's not like that. When you want to apply the concept of the digital twins and all those things into the in particular the railroad infrastructure, it's not easy. It's not easy. We have to develop this kind of the system that I just mentioned through my presentation effectively, and that means the measuring unit that I just mentioned has become the first essential piece that we have to develop, before dream about the digital twin concept for the infrastructure, railroad infrastructure in Thailand.
Right. So in your concept, this spy rock gonna sit in the ballast from the day that you put the ballast until you redo it.
Yep.
How long is that?
I think for the life cycle of the rail tracks or the roads, right? We talking about 50 years.
Wow.
50 years.
It's not just the shape now, the materials that used to make the housing.
Yep, that's right. That's right.
50 years.
Yep.
Okay.
That need to be well designed, to capture all things for the long time. Of course, during the lifetime, we would face with the major maintenance, but it's just like you dig all out and put all in. It's not like that. It's just some part of the fix, right? That means you have to carefully design this thing. But I think this one is at the beginning. It's long way to go, you know. But that's mean hopefully my talk would raise some awareness to MTech, you know, that we have to do something about this for Thailand, because our perception think that the infrastructure is easy, it's gonna be last long, it's gonna exist like that for the whole life, but it's not like that. It changes day by day. We have to build up some system that can understand and capture the real-time behavior of the tracks when the time goes by.
Okay. Well, we hope you the best of luck with that.
Thank you for that.
Thank you for the fascinating talk, Dr. Pirapong. Thank you.
Thank you. Thank you very much. Thank you everyone for your attention.
Okay, we're moving on to our next talk. Our next talk will be by Dr. Sakdirat Kwan Ureun. I'm not sure if I said your surname correctly here. So Dr. Sakdirat is a reader in railway and civil engineering at the University of Birmingham in United Kingdom. He has over 20 years experience in both railway industry and academia. He is also a fellow of Engineers Australia, a chartered engineer in both civil and structural engineering, an academia panel, member of Permanent Way Institute, and a specialty chief editor of Frontier in Built Environment. He has authored and co-authored over 500 technical publications, sits on 12 editorial boards, and is also a member of ISO and BSI Standard Committee for Railway Application. And today, he will be giving us a talk entitled IoT, Big Data, and AI Applications to Railway Systems. So, Dr. Sakdirat, please.
Thank you very much for having me today. If you couldn't see any PowerPoint presentations or couldn't hear what I'm talking, please feel free to speak up, and then I try my best to acknowledge and correct that issue. So
It's great
today,
moment.
thank you very much. Thank you. First of all, I'd like to thank NSTDA and the teams who kindly giving me the opportunity to be here today. Well, I really always appreciate the chance to be able to help people in doing railway research globally. So I'm from University of Birmingham. Please call me Zach if you like. My Thai name is very difficult, so I just leave it as it is. So I will move on. So first of all, I'd like to present maybe where I'm coming from. I work, I'm Thai basically, but however, I work at the University of Birmingham. University of Birmingham has been founded since 1900, so far it's around 120 years. Prior to the University of Birmingham, I worked as a railway engineer for 14 years in the industry. So I spent 14 years in the Railway Authority. We call them, in the past it's called rail corporations. At present, they call them Transport for New South Wales or Sydney Trains, for example. So after maybe 14 years, I gave up my industry and then I come back to academia, and you can see me what I'm doing here. So Birmingham is around one and a half hours from London. Birmingham is the second largest city in the UK, just after London. We have around 2 million, almost 2 million people live in Birmingham area. So this is the skyline of Birmingham. So I will move on quickly. So then you'll be able to see some of the presentations. So I hope I will see whether I can share my videos. I hope it shares out automatically. So I don't have to do anything in particular. So let's see what happens.
Zach, are we supposed to be hearing something?
Dr. Zach, the video have no sound. Is that okay?
So let's. So you cannot hear any sound.
Yeah, you should share the sound as well, Zach.
Let's see whether we can share sound. I cannot share any sound, by the way. maybe I just explain myself.
I-
That would be very funny. However, let me see. Can you help sharing sound from your end? Because I cannot share sound from my end.
หนุ่มได้ไหมคะทำแชร์ซาวให้อาจารย์ได้ปะ
เดี๋ยวลองดูครับเดี๋ยวแป๊บหนึ่ง
หรือว่าผมเปลี่ยนเป็นไมโครโฟนจาก sound
Can you change the sound to the computer?
ใช่ครับ
Dr. Sakan,
apologies
share
for those people.
okay?
Do you want to try to play some? Can you hear something?
Not yet.
Can you hear the music from the video?
No, unfortunately, I cannot hear it.
I see. So I think what I can do is I just explain what it happens, and then you go through with just the video. So apologies for that. I would just turn off the sound and then I play. So University of Birmingham, we home to BCRE. BCRE is Birmingham Center for Railway Research, and we are the European largest railway research lab. We do all kind of research, very comprehensive, from civil, mechanical, electrical, signaling, and social science, as you can say. Social science mean like passengers related research and life cycle and everything. The first hydrogen trains in the UK are actually made at the University of Birmingham. We have won a number of prizes, including the Queen's Anniversary Prize as well. We collaborate internationally, not only in the UK, but we work globally. So people in railways research around the world know Birmingham quite well. We also offer a variety degrees of rail engineering. We are the first university in the UK, maybe the only one, who actually have accreditation in rail engineering. The research that we do cover various topics. The first paper about railways has been published from academic at University of Birmingham in 1970s. We also home to various training center. We also home to various testing facilities, and we collaborate internationally with not only companies, but also with SMEs, like small, medium enterprise, and industry sector. We also won a lot of awards globally and also domestically. We have the university train stations. We are the only university in the UK that has the train station right on campus. And we also home to the test track. We can actually test anything in real operational conditions. So let's move on. Okay, so we will do this shortly. So everyone here is doing research in railways. So we do hope you believe in one thing. Railways are railway is the least contributors toward carbon emissions, as you can see from these pictures. Before we are moving on to the railway research that we are focusing on, the thing that we always have to remember is that everything has a life cycle. So everything we do cover the life cycle or cover certain stages of the life cycle, whether it's going to be a design stage, construction stage, operation stage, or maintenance stage towards the end of life. This is a life cycle. So whatever it is, it's going to be what it is. The things that we have to always focusing on is that we always have to understand where we are in the way that to be able to build any smart system, anything that you try to build, whether it's smart or stupid, doesn't really matter, but it has to be fit within the life cycle. Stupid means, I didn't mean anything stupid, but I'm thinking something outdated. Sometimes the railways track can last very long time. They don't have budget. They to do things that is quite outdated to all the countries. However, in a European country, we are now moving towards to the futures, and we do hope what we do would be able to inspire many of you and be able to create future collaborations between the UK and also people in Thailand and many people overseas as well. So I have a chat. Actually, yesterday we have a chat with people from University of Technology Sydney related to our future collaborations. One thing that we have been point out is that many things that we have working on so far seem to be outdated. Over the life cycle, we haven't considered problems such as climate resilience, for example. We haven't considered man-made hazards. We haven't considered certain aspects, which is now has been asked to be implemented in the enterprise risk management. So asset management, as you probably call them, or maintenance, has to follow ISO 51000. However, ISO is really outdated by now, but some countries, like Thailand, may still pick up on those particular standards. However, in other countries, we have moving on, we have tried to embed it also ISO standard to be able to take care of uncertainties and risks that come from climate change adaptation, for example. As you can see here, there are certain issues that is considered as a classical problem, but we still cannot solve them effectively, or we cannot detect them quickly enough. And if we try to do something as we do now, or we do something, repeat what other people in other countries do now, what will happen to our future? This is a simple thing that has been happened many times in many countries, repeatedly, many times. Things that you should avoid, things that we should not try to repeat still happens because we keep doing the same thing with other people. And we don't learn the lesson from other people. Things that we should do now is we need to learn lesson from other people and be able to move on, further advance what they have, and then be able to make it or equip our railway system more intelligently and also sustainably. That is most important. And if we ignore many things, this is what happen. You or me, I don't want to be in that particular trains, of course, unless you would like to have adventurous lifestyle. You can try to be on that trains, but particularly for myself, I don't want to be on that train because we cannot predict what will happen after that. Well, that leads to what we have done so far. First, people asking, what has railway been doing in terms of data collections of sensor? We try to think about sensors, but do you know that we have collected lots of data already? In many railways, we call them class 1 railways, we have a lot of sensors installed on the track, on the trains, on board and also on site, and also at certain wayside system. So let's look at them. So my apologies for the background noise. This is the last day in Thailand, so I'm actually leaving to the UK tonight, basically. So my apologies if we have background noise because I'm actually at the home at the moment. Well, this is an example of sensors that has been installed on board and on site. As you can see, we have done a lot of work on track, and we have done also work on trains. So on track inspection is the data that we collect from track inspection. On-board inspection is the data we have collected on the trains. We put a lot of sensors on the train, we put a lot of sensors on the track for various kind of monitoring. So track is a system. We cannot consider only one particular component because they are interact. Many people ask me, because I used to work in railway sector, many people ask me this question, if you have a mud pumping, can you still operate the trains? The answer is yes. Yes, big yes. So certain aspect, if we consider only one particular component failure, it may not incite other failure of the whole system. So this is something that we have to understand. We have to understand what is the best operational conditions, what is the safety limit, what is the real safety limit, and what is the serviceability condition or serviceability limit. Most of constraints that we have working at the moment, like you see in the standard, are serviceability standard. It hasn't actually come to the safety limit just yet. But if you're interested in the framework, how we actually conduct sensors, how to collect big data from the total track inspection, you can actually looking at this in this particular publication that we have done so far, or over the long time. The things that you always have to think is that sensors doesn't do anything unless we collect data, unless we use that data effectively and be able to looking at a system thinking approach, looking at multi-criteria in the way that we do maintenance to be able to reduce not only life cycle costs, but also the life cycle carbon emissions. Many things that we have working in this particular arena is that, for example, in many cases, we have a lot of problem with disruptions. We have working on a system or digital twins. This is the first version of digital twins I have done maybe 7 years ago. Not now. People see our publication that's coming out now. we have done that maybe 5 years ago before we publish. What we publish today is something else that we have done maybe 4 or 5 years ago. So this is something that we have to be aware of. What we're doing now is something else. The thing is that railway cannot avoid disruptions, and that is the big issue at the moment for many railway operations or infrastructure managers, and that led us to did some research in this particular arena. In this particular research, we have looking at how we can use data more efficiently in the way that how we can manage the system when we have disruption. We're looking at various aspects. We're looking at track deteriorations model. We're looking at linear model, nonlinear model, and looking at how we can use AI to be able to equip that. And when we have disruption, we should be able to use the model to help us to do predictive maintenance. Predictive maintenance means that we predict the condition in the future, but the main goal is not predictive maintenance. The main goal is the preventative maintenance. If you do corrective maintenance, it creates unplanned maintenance costs, and that costs a lot of money compared to the planned maintenance costs, which is based on preventative maintenance. So many people misunderstand what does it mean by predictive maintenance and what does it mean by preventative maintenance. The main goal is to do preventative maintenance using predictive tools. That is why they call predictive maintenance. And when we're looking at predictive maintenance, we need to be able to, of course, quantify costs, looking at uncertainty and risk, and balance them, and be able to looking at the values. We be able to use machine learning to be able to help us looking at track quality index. Maybe you don't understand the track quality index, but in international standard or in many railway around the world, the settlement is just one part of track quality index. So we have to looking at various defects that happen. It's not only geometry defect, but also component defects, and then combine them into track quality index. And we be able to do that using machine learning and to be able to help us prepare and program our maintenance when we have disruption. We would like to give you an example of how we using AI applications in railway system, because we have done a lot of work in this arena using AI, using digital twins, using various data from the sensors that we have already had in the system. We also equip a new sensors as well. In fact, however, we will not present today, but if you're interested, you can follow our research and we be able to collaborate or discuss at a later stage. An example that we have already done is to looking at, can we actually use the data from the trains to quantify the wheel flats? Wheel flat is one of the key issues. Many people don't understand what does it mean by wheel flat. Wheel flat is happening when the flat is out of route like this. When the train break at emergencies, or when the trains start to slip, when the wheels start to accelerate too quickly, the wheel flats happen. Wheel flats happen on sometimes both sides, most of the time both sides. And this may also create wheel burns on the rail as well. And this create point that create impact loading on the tracks. Most track component has been designed to take care at certain level or to a certain extent of dynamic loads. However, when you actually have impact loads, those values is no longer, those component has to be deteriorated because of this condition. In this particular study, we do as other people, we use the data from trains, for example, axial box accelerations, or using the data we capture from mobile phone that we collect from the trains, for example. We can looking at various spectra of the signal system and be able to train our model and be able to use this AI model to be able to quantify the locations and the severity of wheel flats, for example. This is an example of the AI model or architecture that we have developed. We use a wide variety of AI. People asking us why. It is because we would like to be able to looking at what will be the best model or the best architecture for our AI model for each particular data set. One thing you have to be aware is that the data in railways can be random. It can be randomized, and sometimes certain tactics or sometimes certain methods for AI may not be suitable for that particular data set. So we need to be able to first looking at, maybe we need to tune the parameters within the models. After you do tuning parameter in the model, we call them hyperparameter tuning. We can also change the methodologies to be able to looking at, can we use other techniques? And this is an example of what we have done. The things we have quantified is that we found that certain techniques may not be working for certain data sets. For example, in this particular case, we found that if we use a deep learning, that help us to be able to quantify the wavelets, locate the locations of the wavelets, and also locate the severity of the wavelets quickly. Apart from that, we also working on the combined defects, because for railways, unfortunately, it's not only one component that fail. Sometimes when it fail, it generates impact loadings, and then impact loadings aggravate more problem, ballast brakes, eclipse brake, rail startup even more, and then the rail joints bent. So all kind of defects can happen in vicinities, locations, or even in exactly the same locations. So our research also try to be able to understand that by using the same data sets that we have, not the same data set, but using the census data that we have to be able to quantify the locations, whether the rail defect are combined or different. And we need to be able to differentiate that, because fixing the rail can be more difficult than fixing the wheel, because most of the time you send the train to a depot, and then you can use even a robot to inspect the trains. We have a robot research to do that at the University of Birmingham, to be able to use a robot, inspect the train, and then you can reprofile the wheel very quickly. However, for the rail, you need to be able to understand that the rail cannot be changed quickly. And at the same time, to be able to maintain the tracks, you definitely need to go to certain location to maintain the track, whether it's going to be a component, whether it's going to be a geometry, or whether it's going to be something related to those issues. And that is something that we have to work on. So we have to looking at combination of defects. An example that we have working on is to looking at the combined big settlement, differential settlement with defect from rail joints, for example. This is a key example because the rail joints will deteriorate, and then the impact loading will generate a dynamic effect onto ballast, onto components, and then those components dilate. So for example, ballast is a funny thing. They dilate. Dilate means they spread out. When they spread out, if you don't understand the dilation of the ballast and at different confinement, I recommend you read some work by Professor Buddhima Indaratna from University of Technology, Sydney. He's one of the very pioneer in this area of the field, and one of the best. I would say the best in the area, but I would say one of the best, just to be humble. Yes, this particular aspect is something important, because once you have impact loading, it activates all the system. And when it activates all the system, it's become a compound problem. And that is a key problem in this particular case. So in this particular case, we have to looking at, we call them, we have to develop a more complex patterns of our AI to be able to not only to check one particular problem, but also to looking at sensing whether is it going to be just one defect or is a compound defects. And you can see that there are at least three cases. It can be one differential settlement, one deep joint, and the compound between settlement and deep joints. It can be a short wavelength and long wavelength. So you have to also understand that when you're looking at differential track settlement, we have to consider the wavelength or the roughness of the track as well. You cannot just say that this is a 5 millimeter settlement. That doesn't make sense, because you need to looking at what is the wavelength linked to that particular defect. And this led to our model. So we do similar work. We collect data from the trains, and we're looking at various patterns. We haven't shown you the patterns because I have removed the slide, because I have so many slides. So I need to remove them. Otherwise, I won't be able to finish in 30 minutes time. That is why also speaking very fast as well. Apologies to many audience. If you need me to speak slower, please let me know. But because of the time, I try my best to speak a little bit fast, because I have a lot of slides. And as you can see, we use a various AI techniques, deep learning, DNN, CNN is convolutional neural network, for example. RNN is a retention neural network, for example. You can see that various techniques, even though you do a June's parameter, a parameter that has been tuned, or architecture that has been changed or optimized to be able to get the best accuracy that you can see. But you can see that the best method are still CNN for this particular aspect. Compared to the other, for example, compared to the other defects such as view flag, you see that DNN is better. But for rail, you can see CNN is better. Apart from looking at just the train defect or a track defect, we also working on various aspects of using digital twins and AI, and be able to looking at other research arena. So we also looking at safety and risk assessment at the railway station. So in this particular case, we work with RSSB, Rail Standard and Safety Boards in the UK, and be able to collect some data from Birmingham train station. In general, people don't allow us to collect data at the platform due to, we call them privacy issue. However, in this particular case, we screen out all of the information linked to ID of people and try to work out the best way to be able to get the data for developing our model and be able to quantify a new methods to help doing risk assessment at the railway station without infringing any privacy of anyone at the platform. So we will give you an example. So we cannot show you a detail in this particular case, but we will show you what we have done so far and what we have already been continuing working on. So as I have mentioned earlier, we can collect data at the platforms from various sources of sensors. It can be imagery data, it can be signaling data, it can be data that has been triggered by a station manager. It can be sensors from the track. It can be track circuits, for example. Track circuit locate the location of the trains, but when the train breaks, the track circuits also give a signal telling us that there is something happened at the track, for example. So track circuit can also be used as a sensors. Well, most people actually use track circuit as a sensor to detect the location of the train, but anyway, we will not go into detail because some of you may know this very well, but some of you may not know this very well if you come from different area of research. So we will just say that we use various kind of data. We also collect data from the trains. The trains can come from inspection trains. So many countries has trains that has been equipped with a number of sensors on board. We equip high-speed camera that you take pictures or take pictures, million pictures in 1 second, not million pictures, my apologies, maybe 5,000 pictures or 10,000 pictures in a second, for example, when the train moving along the railway track. We also equip onboard sensors such as accelerations, accelerometers, axle accelerations, the body vibrations, the gyroscopic data, GPS, if you can run the train on the normal track. If you run the train in the tunnel, maybe you have problem with GPS, but you need to use timestamp instead. But this is an example of what we have done. And as you can see, this is an example of the data that we can collect. We can collect all sort of data, and we can use this data to be able to train our model and be able to assess the risk for infrastructures, for rolling stocks. Rolling stock is a moving asset. For electrification assets, and also for passenger safety. We will give you a hint of what we have done. So imagery data can collect from inspection trains, drones, cameras of people. People actually do, when they do engine ride or when they do track inspection, walking track inspection, they take pictures. And those can be data as well. And we can use also mobile phone. We have done a lot of work on mobile phone 7 years ago, using a sensor on the mobile phone to be able to quantify the ride quality and also the location with problems. We're now working on the various things as well with the mobile phone, but we cannot review at the moment. You can also use satellites to collect data of track alignment, for example. You can also use the photogrammetry data and various aspects. This is an example of imagery data that you can use, or we have used already. And it can help us to quantify certain conditions of various assets. So at the same time, we can also use those imagery data and be able to train using, for example, CNN, convolutional neural network, which is very good with imagery data, linked with LSTM, the long short-term method, for example. And then you'll be able to do what we call classification problems in the artificial intelligence problems, and be able to quantify risk, identify what are the risk level, and be able to help people who manage that particular asset. When you're looking at Siemens' presentation at the very beginning, Siemens has a holistic way that one digital twins can help every sector, but in practice, track engineer will not actually have to do rolling stock inspection. Rolling stock engineer will not do track inspection, and they don't maintain track inspection. So you have to understand that stakeholders can be different, and the purpose of digital twin has to be pronounced or have to be vivid for clients or for stakeholders. Because as I mentioned earlier, if you are a customer, people who use the train, you don't care about digital twins. You might care about what is the information you will get from them. But if you are track engineer, you want to looking at the track infrastructure. If you are electrification engineer, you want to looking at electrification infrastructure. If you are rolling stock engineer, you're looking at the moving asset, because everyone has 24 hours a day. You cannot work across too many field of area. That is real practical life, unfortunately. But this is an example. We will show you a case study because we don't have a lot of time today.
Say 2 minutes.
Okay, thank you. Apologies for that. We'll show you a very short case study. For example, we collect data from Birmingham train station to looking at what happened at the train station. We try to avoid all sort of ID people, and then we train in a similar way. We use CNN, and we classify the problem, and then we quantify the risk. Whether it's going to be green is mean low risk, yellow is mean medium, and red can be high risk, for example. So let's move on. This is an example of what happens at the train station. We'll try to blur it out because the pictures we have is very clear, but what we blur it out because the RSSB doesn't like us to make it too clear. So we consult with lots of RSSB operation managers, try to quantify the risk and looking at risk ranking. And also we try to follow ISO standard in terms of risk management. For example, 31,000. So there will be, as an example, as you can see, if you are standing at the platform nicely, you will be in the green. If you do something dodgy or suspicious, you'll be in the yellow, orange, and reds. We move on. We do the same thing. We train our model, we quantify the risk, and then we be able to looking at the performance and predict the risk. So in this particular case, we predict the risk and link to the 5G network to be able to inform the station managers to be able to act promptly. Because if someone acts suspiciously, the system should be able, using the surveillance camera, for example, should be able to inform the station manager to promptly act on certain things. We also provide recommendations on what train station manager should do in this event as well. So the performance that we have done so far for the CNN, we have gained more than 80% of accuracies in terms of the risk event. Sometimes the pictures are blurry. Some people carry something funny. So sometimes the prediction, of course, it is not human. So it only been trained. It only smart as what the data we can given to them. So so far the accuracy is around 80% so far. And over the time, when you run simulation more smoothly, when you collect more data, you'll be able to reduce the loss in the system, mean that the accuracy become better. And then the events that you will try to predict will get more accurate when you predicted those events. Well, I'd like to thank many people who kindly work collaboratively with us and kindly fund us over the times of the projects. And we work collaboratively with many people, also many people who's giving a presentation today as well. And we thanks, and we hopefully we be able to collaborate with many people that we have already established collaborations, and we hope to be able to inspire many people to be able to work together in the future. So thank you very much.
Thank you very much, Dr. Sack, for the insightful talk. And it's good to see that the good old train spotter is back on track again. Unfortunately, we don't have time for any question for today. So if you have any question for Dr. Sack, you can leave it in the chat or send an email. We'll pass it on. And have a safe trip back to the UK. Thank you very much.
Thank you.
Thank you.
Thank you very much. Thank you.
Now we're moving on to our last talk of the day. Oh, sorry. The last talk of the day is by Associate Professor Dr. Alfredo Nunes. Dr. Nunes is from the Intelligent Railway Infrastructure at Delft University of Technology, Netherlands. And the title of his talk today will be Intelligent Railway Infrastructure, Current Developments and Future Trends. So please, Dr. Nunes.
Okay, thank you very much. Can you hear my audio good?
Yeah, I can hear you well, and I can see your yeah.
And the presentation also, okay, perfect. So thank you so much for the invitation to Somrit, Vanida, Karut, that we've been in touch. So I'm Alfredo Núñez. I work at the Delft University of Technology. My research work is in the field of I'm listening some background noise. I'm not sure if it's me or. Okay, I'll just continue.
Okay, there's no background noise on my end. Yeah. I think your voice is very clear at this end.
Perfect. So, well, I work in the field of intelligent railway infrastructure. And basically what I'm trying to do with my team of PhDs and colleagues is to create and to treat actually the infrastructure of railways as a living being. And for that, we will need the railways and this infrastructure to have a kind of brains, which is biologically maybe not possible, but we can do that using the digital world. So basically my research aims for creating those digital brains for the infrastructure so that we are able to communicate with infrastructure, because the infra tries to inform us about different situations, conditions, failures, and what we need to get is our methods that allow us to understand what the infra is trying to say. For motivation, when I started working in railways, one of the first comments I got was that some local defects and rail had a memory. And then for me it was like a bit strange, because usually living beings, they might have some memories. So, but then they said that they had a memory like an elephant, and that even if you remove defects, the track will remember and the defect might appear again and again. Nowadays, we know that that's because probably the defects were not fully removed and there were some remnant cracks or so. So you see that the track has a memory. Also over here, you see what is called the short pitch corrugation. And when the train passes over this defect, it's also called the roaring rail. And because it generates a sound that is super annoying for the people living nearby. So if I'm sharing correctly the audio, you might be able to hear it. Yeah, could you hear?
Yes, we can hear, and it's very annoying.
Yeah, and I'm so sorry, but I should have asked you to reduce a bit the volume of your computers. So, and then you will see then, so the rail is trying to talk. We need just the methods to understand what it's trying to say. And here also, well, you see the locations when there are like loose sleepers and so like the work Sakdirak has been doing. You have responses that could be measured from onboard trains, also sound, and many different sources of information and data. So yeah, that means like, okay, I'm having a sleeper that is a bit loose. So when working in this field of intelligent railways, we do a work that is inherently multidisciplinary. That is that we need the infrastructure domain knowledge in details. So all methods that we provide and we do, they have to be consistent with the knowledge that is already on railway engineering. Further, then, there are also other infrastructure like roads that they have also developed methods before. So in the case of the Netherlands, I would say that the manager of the road infrastructure had implemented solutions in the long term that were very interesting also for the railways. And then we have then also the areas of optimization, systems and control. And that is because the information and decision making is easily systematized by using the techniques from control, so that there is, you connect measurements, situations happening with actions, because you don't want to just collect data for the sake of doing it. You want to know which places should you focus, where to maintain, what to do. And then those actions can be defined by controllers, optimizers, and so. And you know, the railways is a dynamic system, the time variant system, large scale distributed system that changes over time, over locations, and the controllers, they can then support us in trying to get adapted to these new situations. So even if there are changes in stiffness, changes in different parameters, these controllers, they have to get a smart way of getting used to new situations, new conditions, even at the same place. And then finally, we get also the artificial intelligence that is helping a lot in solving problems that let's say that are much more difficult to do for humans, not just for routinary work, but also in trying to find new patterns, new situations, new conditions that we didn't explore before. Just by itself, artificial intelligence cannot be applied to railways if you don't incorporate the specific knowledge from the field. That is, for instance, then if you purely create a database solution based on AI, then the infra manager won't dare to press the button and to let the AI to do the work if it's not something that they can trust, or if the explainability is not clear, or if the physics behind the solutions are not reflected in what the AI is saying. So we have today this challenge on, okay, which infra manager will press the button and let the computer do the job. So, well, Sakdirak also introduced various of the topics I wanted to briefly discuss in this first part, but basically I will very fast try to revisit some general introductions for asset management. Then I will share with you some elements on intelligent railways and some trends and preliminary analysis on the research for AI and the future railways. This is the Netherlands, one of the bridges that will be monitoring. Beautiful landscape. So the motivation then, and I think also all of us are here, is basically that the aging of infrastructures, not just railways, but many others, is challenging everywhere. And we would like to have methods that tell us whether a bridge should be replaced in 5 years, or maybe 10 years, or maybe that has to be replaced right now. So we have knowledge from the physical system, but then also we have now data and more information, predictive models, and so then yeah, we would like to extract solutions and to create solutions based on the information. In the case of Netherlands, and you will see later a video, the railway infrastructure is to be available almost 24/7. So the more you use the infrastructure, the better, of course, but then the more problems. But it comes with the usage, of course, the cost of having more difficulties also for performing maintenance and so. But we need intelligent methods to try to avoid as many problems as possible before they happen. Additionally, the new economy that is based on going to be based on green solution, digitalization, then can also from the infrastructure sector that we can also contribute, because the infrastructures are inherently large scale. Then the solutions that we create can also inspire other fields, can inspire other systems to get better solutions about the green or digitalizations. Here then some brief pointers on railway asset management and also the link with the intelligent system. So we have typically the different infra managers. Some of them, they take care of certain performance, others of cost, let's say cost and performance. So the more, let's say, risk that you take care of systematically, then you might increase a bit the cost in the short term, but in the longer, then it might be that you will get some benefit as well. So this is we have some infra managers that they don't have a lot of budget, let's say, typically rural infrastructure, regional lines, And you need they need, whenever they invest in technology, then they need an immediate return. While we have other infra managers, I would say here Japan probably, that they are already able to incorporate many other challenges, like societal challenges, CO2 and so. And then we have a group here of other infra managers that are going also in this direction by the inclusion of technology. So that's very important for performing research. So to get the new solutions so that we can deal with the different costs optimally. So this was also already mentioned before. So the infrastructure has a service life, typically 20 to 40 years for railway tracks. And they're very difficult processes because they have some degradation mechanisms that are very slow over time. You see it over many years with the degradation here, let's say, and others that are very fast, very fast dynamics that in a day or less could something suddenly change very much. And then in terms of service life, as mentioned before, you have different steps. So since the moment that the infrastructure is an idea, so it's in the brain of someone, that's the moment of thinking of the new railway project. You have also commissioning, installation, then operation, which mostly we try then to operate and to do it optimally, the railways. But then we also have then a moment when we have to dispose the components, to think of recycling, and to feed with information to the acquisition. So then people have to start thinking of, okay, how are going to be acquiring new components. The infrastructures, they have this sort of memory that I discussed before, because the infrastructure will react according to how you treat it. So if you let the infrastructure to not have a maintenance for a long time, then you will see it later that the problems will start to pop up more oftenly. So we have a service life. And particularly in this presentation, I'll be mostly talking about monitoring, maintenance, sensing solutions. So, and then actually, although we work in operation mostly, the monitoring and maintenance is also applied everywhere. So even in the acquisition phase where you design solutions, you already have to start thinking of, okay, what is the effect of having this monitoring system or the policies for the maintenance? One challenge when dealing with data is actually to match what you measure from the systems with what is really happening in the field. And this is something that I like to highlight very much to my, usually I do it with my PhD and my students, is that the data is prone also to noise, to stochasticities, and they might provide information that then if you go to the track and you don't see it, then there's a mismatch. So it's super important and also difficult to validate measurements. But the importance is that that whatever is happening in reality is reflected in the measurement system. And although it sounds normal, natural that it should be that way, it's not always the case. In terms of, well, for monitoring solutions, we have different types of fixed solutions, particular for locations that are very sensitive, like switches and crossings probably. We have the onboard vehicles that they cover a lot of large distances and collect a lot of information, dynamic systems, where you can estimate over many kilometers what's happening in terms of defects. And there's also the crowd-based data. Nowadays, with mobile phones, we can measure a lot of things. So, for instance, the comfort for passengers. Also, the mobile phones are the perfect way to connect directly the infra manager with the passengers. So now they can tweet, they can directly send you a message whenever something is going on. So, and in the presentation here, mostly I will be talking about onboard systems. Here you see a picture of our measurement train. So this is the TU Delft measurement train that we have in the Netherlands, and we've been conducting onboard measurements using this train. And here the train, that it's a measurement train that the colleagues are using in China. So here's some images here of the work we did for a European project like 5 years ago on measuring the mobile phones and the comfort for regional lines. Here is an example on the measurement based on axle block acceleration. And for instance, we have here a very little wheel burn that is when the train passes over this defect, there's an impact that occurs, and the system is sensitive enough to show a time domains difference in the wheel burn. And the faster we go, then the more the energy that we get. So then defects also you'll find at bridges, at different components. So here you see an example then with the colleagues from Southwest Shetland University, the group of Professor Chikang Liu. They are doing great job with AI and the catenary system. So here also, based on video images, you could detect different components. So for instance, there are some that are larger, some that are at the pin level. And with the new technologies, that's something that once you capture the right image, then you can do a lot of analysis and facilitate maintenance. Because then you can indicate the people conducting maintenance to go to the specific location where they're going to find, or they can get prepared with the right tools to fix whatever problem they're going to be facing. So, well, and I said this before, the collecting data for the sake of doing it, it's not so smart to do. And basically, whenever you have measurements or you get information, then that gives you the power to manage things. Without knowledge, without information, it's so difficult to manage, to keep the systems under control. So this is where the systems and control part comes. And typically maintenance is a difficult problem because you perform either two decisions or more, whether to do the maintenance, to do a renewal, or to do nothing. Typically the colleagues think that doing nothing is no decision. You're not deciding, you're doing nothing, but actually most of the time the inframanager decides to do nothing. So it's a decision. Every day, the railway system gets the decision of if there's no maintenance operation, then it was decided to be like that. So, and inframanagers, they require all sort of maintenance strategies. So the reactive maintenance is super necessary. Even if we try with predictive methods to avoid sudden problems to happen, they might happen anyway. So you gotta get ready for reactive or preventive, predictive solutions. Let me see the time. Okay. So, well, there are different solutions for maintenance, and this shows a bit of the timeline. So probably in the future we will have autonomous robots helping us with going into the particular details and solving things, helping people to do the job, railway people doing the job. Over here you see a video of the Dutch railways. You see it's very occupied, and this explains why at TU Delft we have a major work that is being done for many years on board sensing. That is because then any problem that happens here, and the tracks are super occupied, any problem affects a lot of trains. And our vision is that actually nowadays all of the trains, the new trains, are already designed from the manufacturers with the smart sensing. So in the future, we'll be able, like for instance, if we want to monitor one piece of line, to activate the sensing devices for all the trains passing by and to get almost online information of what's going on. But to reach that level of knowledge and that level of sophistication, let's say, then we face many challenges when performing onboard measurements, and that's the research that we are actually now conducting. So this is our motivation then in terms of research. That is to use trains not just to transport people, but also to collect information, infra information. And with that, then in the future we will have all of the trains also serving us as a sensor. So this is the Netherlands, and here you can see our measurement train. So in the field of intelligent railway infrastructure, there are many challenges. And I'm very happy then to see that there are a lot of colleagues also working in railways, doing also AI, doing the intelligent parts. And in my case, I focus my research on those three challenges, although there might be even more. One is perception, that is that to develop methods that allows to assess automatically the condition of the infrastructure. Decision, that is that to let the infrastructure to tell you whether to maintain it or to perform some additional monitoring, and probably later with robots, even do it by itself, and learning from previous experiences, good experiences, also bad ones. But then to be able to keep the system learning, because the railways is a time variant system. It keeps changing over time, and you need to adapt your policies to that. So here I will, I don't have much time, I see, but I will quick share some of the research that I've been in one way or other involved. And I will let this presentation also to be available for you to check later if you want. And I'll be available for questions via email, so feel free to contact me. So as for perception, then the previous presenter also discussed some the big data issues. So in railways, we get it's a large scale system. We get a lot of data in volumes, but also the variety of the data is one of the most difficult things to deal with. So that different sources of data to match them and to make coherent assessment of what's going on. And then there are plenty of methods for fusion, but you need the method to fit to the railway application. So purely based on data, then without the railway's knowledge, then you will get solutions that are not interpretable, and those they will be difficult for infra managers to trust. In perception, then we work since 2013 on neural networks for detection of rolling contact fatigue using axle box acceleration and for detection of defects. And then those works then got later published many years after. So there's also this gap of publication and results. So here we used those neural networks for detection of defects, and we embed it into also the decision making. So you will see if you go to those references, the implementation of neural networks, deep convolutional neural networks, plus the decision making. So because for us, the important is not just the detection of problems, but also suggestion of what to do with them. And that has to do with decision. This was done with the null architecture for deep convolutional neural networks. There are nowadays, I've seen a lot of colleagues working on the similar problems and proposing now the state-of-the-art networks, and they get every time better and better results. So that's fantastic. In that time, we got some defects that were not possible to get detected with the training of the network, but I'm sure that nowadays with these kind of problems then are easily solvable. So this is like a 10 years old ago challenge. So also we have a colleague, the PhD researcher Wasamon Pusakul Kayorn, that she's working also in the AI for railways and implementing solutions that incorporate the third generation neural networks to detect and to find early defects. So she's developing some technologies for spike neural network. Here you could see then the online detection, let's say, for predictive results, trying to find defects as early as possible. And then by using neural networks plus some physical information of the defects, then it's possible then to increase very much the detection. So she's also working on interval modelings to quantify the uncertainties on the predictions, which is super important because the measurements, they have variabilities on speed, on measurement conditions, the loading of the passenger trains, and also the parameters of the model. They have all certain uncertainties that Wasamon is working on to make a more, let's say, interpretable result for detections. So I'll skip the comments. You can see them later. In terms of decisions, so I see it's already time for me to start stopping. So I will quick pass through the next challenge.
You can have 2 minutes.
Okay, thank you. So in terms of decision, then the question on whether to monitor, where to do it, it's a very complex problem. Typically, very easily becomes a non-convex optimization problem. And for that, you need mostly heuristics. We used before evolutionary computation solutions for multi-objective problems to create a ranking for the inframanager, because we knew the problems, but then they need to know where to actually go right now. So with the methodology on evolutionary computation, then we managed then to suggest them places to go. And then we implement this in we measure this passenger line between Brasov and Sarnetsi in Romania. And then we gave this information to the inframanager. We have also then a PhD researcher, a colleague, Sivarak Unsiwilai. He's also working for the development of KPIs based on intelligent systems for transition zones. So he's been monitoring many bridges, capturing the effects of the dynamic measurements, and proposing KPIs for the monitoring of bridges and transition zones. A final challenge on learning, because from the past there could be some, let's say, decisions that are wrong, let's say, but then if you can incorporate it over time, then the system keeps improving. In learning, then there are many technologies and solutions. So colleagues from Southwest Yatsen University, Professor Chekan Liu, the team have been also developing for the catenary system the 3D convolutional neural networks and state-of-the-art solutions based on AI. Here is the research then of Dr. Jumping Song. By using deep convolutional neural networks, it was possible to get also these images, yet the most informative part of the image was not automatically done by the method, so that then he created this, based on reinforcement learning, a way to find the box that has more information. And this is a super interesting and pretty research that the colleagues have done. So let me continue then the development of digital twins, and there are so many different ones that could be used. Then that's something also that nowadays is more and more the standard. So that based on the digital world, you click over the locations, you see actual measurement, you see online measurements, models doing prediction, and that all has to be to facilitate decision making. So multiple challenges here. Now I will try in a minute to indicate some general research in AI and trends. So when working on AI, then we observe almost exponential growth in terms of publications, which is fantastic in the field of railways. Mostly we see linear regression being applied, neural networks as well, and we have fuzzy logic, clustering, transfer learning, also methods that colleagues are also employing to solve railway-related problems. Depending on the component, we have more or less the methods being applied. So for track, for instance, most of the methodologies are based on linear regression and meta-heuristic, so like optimization based on genetic algorithms or PCO. While there are methods, for instance, in the case of crossings, that you see that there are less research being conducted using, for instance, fuzzy logic, which is surprising because with fuzzy logic you can interpret the solutions from AI. So we have many future trends. Let me skip this part. So there are some selected remarks, final ones. Infrastructure is one of a kind system, so it changes over time, also per location. We have so many different sources of degradation at the same time that when developing AI, we would also like to separate the cost of the defects. And this is a further research that has to get conducted, so to be able to interpret the AI solutions. So let me skip this part. I would like to invite you all, you're all interested in railways, in visiting the this
Take this guy.
the MOOC.
He overslept by 35 minutes, ran 531 steps.
So we Theodore created this MOOC for general people. You can take a look. We give it this twice per year, and you can get an overview of very well topics. So that's the invitation. And well, today I'm right now in Sweden, and I record a video for this presentation, but I managed to find a colleague that could go to the field for me today, so I could be with you live. And then we measure already about 500 kilometers of track. We did it 2 times. And this is iron ore line where with the project into track 3, we measure based on axle box acceleration locations where they have rolling contact fatigue, and we are also monitoring track stiffness and the condition of the different components. And then this is our some pictures from yesterday. We did a measurement campaign that was cross border, so we could measure in Sweden and Norway. And that kind of initiative then at European level are super important, because we would like to break all the borders also for the railways. So thanks a lot for your attention, and I apologize for taking more time than I had.
Thank you very much, Dr. Nunes, for the enjoyable presentation and for making time to give us a talk today. We don't really have time for questions from the audience, but as always, the chat box is open, and we got his email address, so we can always contact him. Just a quick comment from me though, as all day today, people have been talking about a holistic approach, how all things are connected in the railway system, but it's not until your presentation when you mentioned that it's like a living being, a living thing, that it makes a lot of sense to me. And for that, thank you very much for the talk today. Now, everyone, don't go yet. The organizer would like to take another photograph. So could everyone turn on their camera? Okay. Rồi, aoยัง?
Two, three. One more. 1, 2, 3. Okay.
Okay. Well, as a representative, as an organizer, we would like to thank all the speakers for today, and of course all the audience who have attended everything running on time and very smoothly. For that, thank you very much. And for the technical team, that we hardly have any technical issue really today. So it was a success. Thank you. And good night.
Thank you so much. Thank you so much. Okay, bye-bye.
Bye.
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 Smoothly down. Để như đầu tiên